Welcome to our webinar, and we are today talking about eSpire Nano. We're going to be doing design and installation overview. My name is Avtandil Giorgadze. I'm a senior product manager, and previously we were talking about eSpire Nano as well, but we were more of doing like introduction on overview. We'll briefly go over that summary today as well, but I'm going to try to make it as brief as possible so that we are not really wasting too much time on that. So eSpire Nano consists of two elements, right? It has the inverter and it has the battery, and together they create eSpire Nano system. Now, what is eSpire Nano? eSpire Nano is a multifunctional and modular scalable system, which is solar and generator ready. It has advanced features, which we're going to expand on later down the road. And it is really a big, strong, but also compact three-phase CNI energy storage system. Now, it is directly compatible with 480 volt Y configured three-phase and also 208 volt Y configured three-phase AC signals. There are three models of this inverter. One of them also can do high-leg delta, so that will be three-phase four-wire delta configured system. But it can only do it with grid-tied mode, just importing, exporting, doing self-consumption, but no backup whatsoever. Those are the three-phase signals that we want to focus on, but obviously it can do much more. It's just these are the most relevant ones in the North America and even more specifically US and Canada maybe. I'm not too familiar with Mexico's grid regulation, but I was assured that the grid AC signal types that are common in Mexico, this inverter can easily cover. So this system works in self-consumption, backup, extra priority, off-grid, peak shaving, time of use, and advanced EMS-controlled modes of operations, right? All of them should sound familiar to you if you are considering this product, and especially if you're attending the technical overview of it. The only thing that really would seem like an outlier for perhaps some of you would be advanced EMS-controlled operation. I'm going to mention a couple of words about that now, and we'll try to talk about that a little more in detail later. But I don't want, again, to spend too much time on this because we are overviewing the hardware itself and its capabilities and what to connect where, not the different tiers and packages that exist for it. And I believe there is another webinar specifically dedicated to EMS controlled operation. But I can tell you right now that advanced EMS controlled operation means that you can do even more complex peak shaving strategy. You can do even more complex and more specific time of use schedule. And you can also monitor external circuits, and you can have AC coupled PV remote from the inverter and still monitor it and still control it. That is what the EMS controlled operation brings to the table as a value proposition. Also, this system can be directly connected to DC coupled PV. So you bring the PV strings and you utilize the built-in MPPTs to turn that PV production into useful AC. It can also do AC coupled PV. It can do both at the same time, by the way. It can facilitate a generator integration, and it has a smart load feature. In a sense, you have a controlled backup output for one particular load or load circuit. Furthermore, we mentioned that it can do DC coupled PV, but that's not all. It has built-in APS RSD transmitter for the DC coupled PV, which can but what it really does is that it eliminates extra work of putting in the transmitter. And what is expected of you is just to add the receivers or MOPs behind the electrical panels, compatible ones to the APS transmitter that will have built in, and that's it. Then power line communication can exist. I mentioned generator. We have dedicated 2 R-star ports for a generator. I'm going to show that later. We have percent SOC and grid availability base control for the smart load circuit. That's what I meant when I said that one specific load or load circuit output to which you can control based on certain conditions. Those are the conditions: percent SOC and grid availability. You see the summary of the certifications. All of these are pretty much relevant ones, and we have them all. Yeah, that's really all there is to this. Now, the star of the show when it comes to all these modes of operations and integration and capabilities, that all comes down to the nano inverter, because battery, if you really think about it, it is just a system that stores your energy. But how that energy is managed, released, and so forth, that comes down to the inverter. And because this is a hybrid inverter, it has much more capability than just inverting DC to AC or vice versa. Just quickly, let's go over what we have in terms of the inverters. We have 3 models available. One of them is 30 kilowatt 480 volt inverter. We also have 60 kilowatt 480 volt inverter, and we also have 30 kilowatt 208 volt inverter. And this 30 kilowatt 208 volt inverter is the one that can do high elect delta, but with no backup. The other 2 are strictly dedicated to what they show, and also certain other variations depending on area in which it will be deployed. But let's be on the point. We are focusing on 480 volt and 208 volts for now. Maybe we're going to have more webinars and more technical overviews for certain geographic areas and the AC signals applicable and commonly used there. So PV input for 30 kilowatt inverters is identical. So on the DC side, when it comes to the capabilities of handling the PV on the DC side, the 30 kilowatt inverters are identical. They both have 3 MPPTs. 60 kilowatt inverter has 4 MPPTs. These MPPTs, whether you have 3 of them or 4 of them, depending on the inverter type, they are identical. So MPPT voltage range is the same, input voltage is the same, quantity of inputs per MPPTs is the same, 2 per MPPT. And MPPT can handle 42 amps of continuous current, but there may be no more than 20 amps of continuous current per input. And 1000 volts as the maximum PV input voltage, that is very straightforward. That's what you're allowed to have in the commercial application, and that's why the inverter, this being a CNI inverter, has to accommodate for those 1000 volts as well. MPPT voltage range is the voltage range in which the inverter actually performs maximum power point tracking. Short circuit currents are also given here, 65 amps. Battery charge and discharge currents, as I said, DC side is identical between 30 kilowatt inverters. Both of them can do 33 kilowatts of battery charge and discharge. Where they differ, though, is on the AC side, right? So the 30 kilowatt inverters, yes, they are both called 30 kilowatts, but the 208 volt inverter can only output 26 kVA, and the 480 volt 30 kilowatt inverter can output 30 kilowatts, right? That all comes down to current and how the power is calculated based on current, because you'll notice that AC output current is different between them, and rated AC output current for 480 volt inverter is 36, and for 208 volt is 72. So in those terms, 60 kilowatt and 30 kilowatt inverters are much more similar in terms of current than 60 kilowatt 480 volt inverter with 30 kilowatt 480 volt inverter. So, but AC side current capabilities are not only influenced by current, but also by voltage, because both of them are considered when determining power for the AC. So because you have 208, you multiply by 208 and square root of 3, and that's how you get 26. And if you multiply 72.2 by 480 volts and then square root of 3, that's when you get 60 kilowatts. Maximum output current is also variable in a sense that, yes, continuously it can output 26 kilowatts for 208 volt 30 kilowatt inverter, 480 volt 60 kilowatt inverter can do 60 kilowatts of output, and 30 kilowatt 480 volt inverter can do 30 kilowatts of output. And that translates to 72.2 amps for first two inverters that I mentioned, and 36 amps for the last one. But for shorter periods of times, it can increase its peak output by quite a bit. So your 36 amps for 5 minutes becomes 43.3 for the 30 kilowatt 480 volt inverter, whereas 72.2 becomes 86.6 for 5 minutes, right? And that is significant, especially if you have some kind of equipment that at the startup has a bigger surge, but then that surge goes away, or gradually the peak demand is reduced. You might find this feature of the inverter useful. So now that you have kind of understanding of what the performance capability summary is, let's talk about more hands-on stuff, right? So the Nano inverters are wall-mounted, and they are wall-mounted using their bracket only. So there is no other valid method by which you can wall-mount the Nano inverter. You have to use that wall mount bracket, and once that wall mount bracket is affixed to the appropriate surface, which should be horizontal, and the bracket should be flush against that, or vertical, and the bracket should be flush against that vertical surface, then you can hang the inverter onto it. Now, you can only have 6 Nano inverters working in parallel, and they must be of identical type. So you cannot mix different types of inverters. All of them must be of the same type, the same model. Each inverter can work with up to 3 batteries. By up to 3, we also count in 0, because you may have a situation when you have, let's say, 2 inverters working in parallel, and one of them does not have batteries at all, and the other one does. That is a possibility. You can do that. But no matter whether or not you have 5 inverters in parallel, or 4 inverters in parallel, or just 1 inverter, you cannot have anything more than 3 batteries of identical type working with that 1 inverter, right? So you cannot have 40 kilowatt hour and 60 kilowatt hour batteries mixed together and connected to 1 inverter. That unfortunately is not allowed, although you can have multiple inverters, each with its own type of battery. So for example, if you have one 60 kilowatt inverter and the other 60 kilowatt inverter, one inverter may have, I don't know, 240 kilowatt hour batteries, and the other may have 160 kilowatt hour battery, because these batteries are not connecting in parallel, which means that the voltage difference that they have is not going to produce any problems, because the inverter will manage the power flow to each of them, but you are not paralleling them. So one will not backfeed into the other because it has higher nominal voltage than the other. And 2 Nano inverters never, ever are allowed to share 1 battery or multiple batteries connected in parallel. Very straightforward. When multiple Nano inverters are working in parallel, there may be 1 or more inverters without a battery connection. I mentioned this already, but again, this is appropriate. You can have 1 or more inverters in the parallel group of the inverters without any batteries. Why you want to do that? It's a different matter. Maybe you are not going to need any more storage now, but you have plenty of PV, but you are expecting that later down the road, in about 2 or 3 years, you're going to add another battery, and you want to reserve that ability to utilize all the PV that you have and have the system ready for the battery side expansion. Totally fine. Another thing is that you might decide that, well, yes, Fortress Power does allow me to have a Pro package in which I will have AC Gallo PV inverter controlled by the other 2 inverters, but I think it's more useful for me to have 3 inverters, 2 of them with batteries and 1 of them without the battery, because what if, I don't know, 5 years down the road, I need more capacity, that type of thing. Like, case by case, people have different reasons why they want to do this or not do this, for that matter, but it's always good to have this capability. And regardless of whether the all of the inverters or some of the inverters have batteries connected to them when in the parallel inverter group, all of them must connect to the same AC panels with same AC ports, right? So if you have a backed up load panel, all of the inverters connect to that backed up load panel. If this is a grid-tied system, all of them connect to the panel board from which they take the grid AC power. I'm going to give you an extreme example. Let's say you have a generator and you have some inverters without the batteries and some inverters with the batteries. Even the inverters without the batteries will connect to the generator AC output, right? Because that's the rule. They all need to detect the same AC signal. Otherwise, you might encounter faults and not that great of a user experience. So please keep that in mind. Also, I mentioned before that it is possible to have different storage capacity per inverter, provided that each inverter has only one type of batteries connected to it. And I brought an example of, and I provided an example of one inverter having 80 kilowatt hours of capacity coming from two 40 kilowatt hour batteries, and the other one having one 60 kilowatt hour battery. Well, yes, that is totally valid, but also the inverter has to manage the power between the batteries and do its best not to have one depleted quicker than the other, because in that case, you will not only lose some capacity that is not available to you. I mean, if you discharge a battery long enough, that's inevitable anyway. But what's going to happen is that the battery or the inverter, which batteries have been depleted, that inverter will not function. So yes, you lost some of the capacity, but that was expected. But you also lost some, or in this example, half of your power output capability, right? So one of the ways we try to ask our customers to mitigate that is to have PV distribution being proportional to the storage distribution between the batteries, right? So we have 60 kilowatt hour and 80 kilowatt hour in our case, right? So, well, how would you distribute the PV between these? So if we take 80 kilowatt hour as 100%, right? 60 kilowatt hour then becomes 3/4 or 75%, right? So you would have 75% difference between the PV distribution as well, right? So that way, all of them receive PV power proportionally to their storage size. Otherwise, if 60 kilowatt hour system is receiving considerably less power than the 80 kilowatt hour system, what's going to happen is that 60 kilowatt hour system will deplete faster and charge later, right? So proportional distribution of PV is the way to go. So all Nano inverters are compatible with all Nano batteries. As I said before, in our example, 60 kilowatt inverter was working perfectly fine with 160 kilowatt hour battery, and it was also working fine with two 40 kilowatt hour batteries. In some certain rare cases, the battery storage system could be requested to be undersized in the sense that you will have 60 kilowatt inverter, but let's say 40 kilowatt hour battery, but the inverter's power input and output capabilities are greater than that of the battery. Well, that is a risk, especially if you're doing a backup. There is a risk that the inverter will overcharge or over discharge in terms of current to battery. Yes, battery does have protection mechanisms against that, but on the other hand, there's no much protection mechanism against the load, because the load, when it turns on, it instantly requests power from the inverter. The inverter passes over, so to speak, that request towards the battery, and the battery has to respond. Yes, it will go offline from the inverter and separate from the inverter if overcurrent occurs, but relying on the safety mechanism, so to speak, is the same as relying on the guardrail rather than a steering wheel. if you're driving a car, right? You don't want to do that over and over again. So for grid-tied solutions, when you have like undersized battery bank compared to the inverter, that's very straightforward. You're just gonna enter charge and discharge limits appropriately so that the battery is not overcharged. If you have load, there must be hardware guarantee, breaker of some sort, that or fuse for that matter, that whatever the battery can output, the load cannot demand more than that. Now, someone could be asking, well, if I need to be so careful, if I need to derate my inverter capabilities as far as the battery charging and discharging goes, why would I bother having this type of system? Well, sometimes people want to go really, really extreme on the PV size and have it quite large, and the battery size doesn't matter to them that much because much of that PV production is consumed while it's being produced, right? That type of thing. But again, this is all about giving our customers flexibility. Fortress Power, the way I see it, the way I hear it, and the way I believe is famous for giving people as much flexibility as we can. And this is in line with our approach. All of these things that I told you about. We could cookie cutter and have limitations, but no, we don't want to do that. We want to have, yes, some limitations, but as few of them as possible, right? And that allows that flexibility, and that approach allows us to have a very versatile system and very much modular system. So I know that in this industry, everyone says, oh, it's modular, it's scalable. Yes, true. But here's the extreme example for you from Fortress Power, and specifically based on the Nano energy storage system. You can start with as small as 26 kVA power output and 40 kilowatt hour nominal storage system. That will be your one 30K 208 volt inverter and one 40 kilowatt hour battery. And you can go up to 1.08 megawatt hours of storage and 360 kVA of power input and output capability. And even more on the PV side, if you think about it, that will be 600 kilowatts on the PV side. That is huge, right? For small commercial, it is huge. Obviously, we have some systems that are like multiple megawatt hours and can be multiple hundreds of kilowatts. But for such a small system to achieve this, I think it's quite remarkable. And just like I said about 26 kVA 40 kilowatt hour system, let me also describe how this 360 kilowatt or kVA and 1.08 megawatt hour figures are arrived upon. So 360 kVA comes from 660 kVA or 60 kilowatt 480 volt inverters, and 1.08 megawatt hours that comes from 360 kilowatt hour batteries connected to each of these inverters. So you have 6 inverters, each one with 3 batteries. You have 18 batteries, 18 times 60, that's 1.08. Well, 18 times 60 is not 1.08, it's 1080. But if you convert it to megawatt hours, it's 1.08 megawatt hours. Now, what's included with this inverter? Obviously, there's a wall mount bracket. Obviously, there are fastening screws, expansion bolts. There is a communication dongle that allows you to use our awesome app. The one that is very user-friendly. It is our latest and greatest, very straightforward, amazing graphics, very functional, easy to understand. We don't have a manual or a text guide for it. The reason being that it's so self-explanatory, we don't see the need. We have screw-in handles to kind of make it easier to maneuver this thing around, as well. You will see later. This thing is almost 200 pounds. It's quite heavy. You have Rogowski coil set. You have 3 of them because we are working with 3-phase. Now, that's what you get by default. And with standard package, you can get no more, right? You can only have 3 CTs because these CTs, their sole purpose is to monitor the total import and total export. Granted, you can get bigger CTs than 600 amps. You can get 800 amps, 1200 amps, 1600 amps. I think all the way up to, I know, all the way up to 3000 amps. That's what you can get. And this being UL 3181 certified inverter, all these CTs alongside with the meter that we're going to get to in a second, those are listed on the certification. So even if you change 600 MCTs with bigger CTs, provided that those are the CTs that you have requested from us and we have provided to you, and those are the CTs that are listed on the certification, you are retaining that UL 3181, right? Those CTs do not connect directly to the inverter, though. Those CTs connect to the meter, and the meter communicates to the inverter. And that's how that thing works. And also, it's maybe I should mention it later. I will probably mention it later anyway, because I think I have it on one of the slides. But the CT signal cables from where they deliver that analog output to the meter, those cables cannot be expanded. So you have the CT to meter distance limited by the length of those analog cables, which we will see that we will check later together. I believe that is 4 meters, which is almost like what? However many feet. I think it's 4 meters. But the meter to inverter communication, that can be up to like 300 feet. So that's no problem. So if you have this situation where you have the electrical panel or main panel board, or the meter for that matter, far away from the inverter, the way to go is that you have meter and CTs close together, and then long communication cable going from the meter to the inverter. Then some of the tools that you may be using, all of these should sound familiar to you or seem familiar to you. Phase rotation detector, though, that for people that have not extensively worked with three-phase applications, that could be something new. Now, in single phase or split phase applications, we don't use phase rotation detector because why would we? It's a single phase split in two. There's no rotation that is happening between the phases, at least downstream of the meter. But here we have 3 phases, and phase rotation must be correct. It must be clockwise. And phase rotation detector allows you to determine whether or not it's clockwise the way it connects to the inverter. So L1 to L2 to L3, that should be clockwise rotation, and that's how it should be connected to the grid side of the inverter. And same applies if you're connecting a generator, AC coupled PV. Although I do believe AC coupled PV automatically adjusts, but don't quote me on that. In any sense, you need to use phase rotation detector. This is a must, and it's not that expensive. One of my colleagues was traveling for work and had the phase detector with him, and we needed one in the lab. We managed to order one from Amazon for, I think, less than $50. So it's not a huge deal if you consider the total cost of the system and the tools and everything else. No. We mentioned the tools. We must also talk about where you install it with these tools. So the inverter may be secured onto the battery enclosure, or may it be secured onto some other random wall. It doesn't matter. The inverter is outside, right? And this is not an inverter that has its own separate enclosure, which is climate controlled. No, that's not the case. It's just an air-cooled hybrid inverter. Granted, amazing, very functional, quality made, all of that, but still, it's an air-cooled inverter, and ambient temperature will have effect on it. So minimum ambient temperature to which it should be exposed is minus 25 degrees C or minus 13 degrees Fahrenheit. Maximum ambient temperature should be 140 degrees Fahrenheit. Relative humidity, this is very common in our industry, up to 100% non-condensing. If you're installing this inverter in the northern hemisphere, it should not be in the south-facing wall, unless there is adequate amount of shading, so it's not exposed to the direct sunlight for the entire day. And if you're in the southern hemisphere, it should not be installed onto a north-facing wall, right? And for obvious reasons, if it's constantly exposed to the direct sunlight, that screen is going to burn. The inverter will struggle to cool down itself. So, again, please do follow these rules. They are there for a reason. If you have adequate shading, that's fine though. What we're trying to prevent is direct sun exposure. Other things about what not to do is there should be adequate air circulation because, again, this is an air-cooled unit and air has to circulate around it. Otherwise, it's going to create its own microclimate, so to speak, warm up the air around it if it's in a small electrical room. And the more it tries to cool itself, the more it increases the temperature of that air, right? Air around it. So air circulation is a must. If you are putting the inverter on the side of the outdoor battery unit, I mean, there is circulation for the inverter, right? There too, there are clearances, and we're going to get to that. But in any case, you should be mindful of the fact that this stuff is not liquid cooled and the cooling system is not somewhere else. The battery is equipped with an HVAC, and that itself needs some air circulation around it, and the inverter is air cooled, so air circulation is needed. Quite obviously, in a living area where prone presence of people or animals is expected, you don't install this inverter. I don't know if anyone would actually try to do this, but that is the thing. Near flammable substances, the nano inverter must be at least 10 feet away from any flammable substances at all times. And although the wording here suggests that the system must not be installed at a higher elevation than 8,208 feet, that is not quite true, is it now? Because we can derate the inverter, and then you can have it at higher elevations. It's just at this elevation, we need to start considering derating the inverter. Again, that depends on your usage pattern, right? Because usually my approach is, let's deploy the system, let's monitor it, especially if it's like new development or something like that, and we have no idea how much power will be used and at what rate, for how long, that type of thing. Let's monitor the system. If we feel like, oh, it's running warmer than we would like on average or median, then we're going to consider derating. But derating is an option. You can go by higher elevations. At some point, we'll also develop a suggested derating percentage per increase of elevation beyond 8,208 feet. That is not ready yet, but we're working on it. And because, I mean, again, this comes down to the fact that this is an air-cooled unit, and the higher the elevation, less the density of the air around the unit, and lower the density, lower the cooling effect. And technically, you can mitigate that with higher speed, but these fans on the inverter can only spin so fast. Clearance requirements. Here they are, very straightforward. One thing I want to note, though, these are clearance requirements, obviously, that are to be followed. And if you're putting the nano inverter on a wall, you will refer to this. And this is also given in the inverter manual. I personally put it there. But one important thing to mention is that you don't need to do a lot of mental gymnastics to determine whether or not you're within the clearance requirements. If you're putting the inverter on the side of the outdoor battery, by definition you are. Because it so happens that if you follow the proper battery clearances, you are automatically following the inverter-to-inverter clearances as well. So please keep that in mind. Now, inverter installation nodes. I mentioned some of this before, but it doesn't hurt to repeat. Hopefully we're good on time. We're not that good on time. Maybe we're going to do part 2 of this thing. Because previous time when I tried to do this webinar, it went too long. I'm trying to not get into extra details of the things, but how successful I am, I don't know, because I'm not reading. I'm speaking as I go. If we are gonna see that we're not handling this well in an hour, we're gonna have a part 2 scheduled at some point. So Nano inverter must be installed such that it is mounted on the wall bracket. As I said, you mount it on the wall bracket, nothing else. The wall bracket itself you affix to the wall or some kind of other vertical surface, and that surface as you see on the slide. That surface must be that surface or wall or structure must be able to withstand 4 times the combined weight of the inverters on that structure, right? If it's one inverter, total weight of one inverter. If it's 4 inverters, total weight of 4 inverters multiplied by 4, or one inverter weight multiplied by 4. That's what it's supposed to withstand. But the bracket onto the surface must be vertical, and it should be flush against the surface so that it's not tilted, inclined, warped, bent, nothing like that. On the bracket, dimensions of which are given right here, hopefully this will make it easy for you to kind of determine where to mount it and what amount of space is needed. I also included this in the inverter manual, by the way. This arrow should be pointing up always. That is a proper orientation of the bracket. Sorry. And use 4 fasteners to secure them in place. 1, 2, 3, 4. And also, if you have this type of scenario when there are multiple inverters on opposite sides of the same wall or structure, that structure, as we said, must be able to support 4 times the combined weight of all the inverters that it's supporting, and the thickness of the wall, i.e., the distance, horizontal distance between the two brackets, should be no less than 12 inches. Am I missing anything? Did I say everything? Yeah, I think I covered it all. So, inverter installation notes. These handles I mentioned before when we were talking about the inverter packing list. These are screw-in handles. They go on the sides right here, and you just screw it in. Hand tight is fine. These make it easier for you to kind of maneuver the inverter in the field and raise it and so forth. You can use these handles with like a crane with straps. That's also totally fine. You can also remove them once you're done installing the inverter. Although, for example, when we were installing it in our lab, we did not remove it. We kept it in place, and I cannot say that it is aesthetically displeasing or anything like that. It looks fine even with the handles on, although it serves no purpose once it's installed permanently, at least not until the day of decommissioning, which will be hopefully tens and tens of years later down the road after commissioning. Yeah, what else I want to say here? Yeah, inverter is, as I said, 200 pounds. One person is not lifting it, and you might need special equipment, or at least 2 people, depending on what those people are comfortable with doing. If they're comfortable with lifting 200 pounds and putting that on the wall onto the wall bracket, that's fine. But I would strongly recommend using power equipment. Some kind of portable crane could be used. Lift jack, if you can find the one that is useful for this purpose, that can be used. Forklift could be technically another option, but I would not recommend it. In our case, for example, we managed to raise it and put it on the wall mount bracket using a engine hoist. We had one random one laying around in the lab, and that did the job perfectly fine. Yeah, and obviously you handle this inverter with care. You don't want to drop it. You don't want to hit it against anything. Be gentle with it. It's still, yes, it's solidly built and everything else, but it's just a human-made object that can be damaged just like anything else, especially considering that it has this dongle thing sticking out here. It has the EPO button sticking out on the other side. It has the DC switch right here. It has plastic caps on the bottom instead of the metal knockouts. And I mean, as I said, it's 200 pounds. Even if you drop it a couple of inches above the ground from that height, you'll still manage to bend it. Mounting the inverter onto the bracket. So we presume that the bracket is onto the wall, following all the requirements that we were outlining before. Then it has almost this kind of a lip, and the inverter is hung on top of that lip, right? Just like you see right here. And then, so that that lip doesn't become the axis of rotation, you put in two screws in the bottom of the bracket, one on each side, and voila, the inverter is secured in its place. Now, the ports. These are the ports. They are labeled for what they are, but it's not mandatory. Well, ports are mandatory to be used as they are labeled. We're going to see that in a moment. But inputs, you can use them differently if you want, right? Depends on your application and what you're trying to do. So use it as you need to some extent. If you use the inverter in a way that it is mounted on the exterior wall of our outdoor unit, some of it is predetermined for you. So these three will be occupied by default, and these two will be reserved for PV, and then you have backup and grid. So not much choice, but it doesn't matter to us which input you use for what. What matters to us is that the conductors are grouped together in conduits properly, following the NEC code, and that all the conductors end up at the appropriate ports or terminals. Then, communication dongle on the left side, it goes to the bottom. There are 4 screws to secure it in place. You have a PV disconnect switch. Again, this is not a rapid shutdown activation switch. It's a PV disconnect switch. So high voltage still exists. EPO it's just it doesn't find its way to the inverter. MPPTs. EPO RSD switch. EPO RSD switch is actually what activates the RSD and also prevents power flows as needed, so that once you press it, it goes to an emergency power off. It remains offline, or I'm sorry, online, but some of the circuits are offline and the RSD is activated. Now, the ports, the ones that I mentioned. There's a ton of information on the screen. You can read it, but I will go over them one by one. So let's start with number one. Number one being our MPPTs. The extremely observant ones of you will notice that this has 16 inputs, which means it has 4 MPPTs, which means that this is the photo taking on a 60 kilowatt 480 volt inverter, which is true. This is the one that we have in the lab, and it has 4 MPPTs, just like 60 kilowatt inverter is supposed to. And this is what I meant. You have 1, 2, 3, 4. These 4 ports are for MPPT1. So you have PV1 plus, PV2 plus, PV1 minus, PV2 minus, right? So that type of thing. And continue with the other MPPTs. You also have PV ground bar. In most cases, I don't foresee this being used, but I mean, it's there. When you're grounding this, please always follow the NEC code. It's very important. Don't create like separate ground just for PV and not ground it to anything else. Don't do that stuff. That code is there for a reason, and that is there for safety. Please do follow that. But again, we have this ground terminal here, which I don't foresee being used. But again, if need be, it is there. We have number 2. Those will be your battery ports. So battery 1 plus, battery 1 minus, or I'm sorry. Yes, battery 1 plus, battery 1 minus, battery 2 plus, battery 2 minus. All these 4 ports will be occupied when you're dealing with the Nano system, right? So you'll have 2 positives going to the primary or single battery, depending on how you have the configuration. And some of you might think that, oh, it has to, especially ones that have worked in the residential department before, like I have, for example. Once I saw this, I was like, oh yeah, probably this serves as a bus bar. No, it does not serve as a bus bar. So if you are going to walk up to this thing with your meter and try to measure continuity between 1 plus and 2 plus, there is no continuity. Certain settings must be entered in the inverter so that it creates the simulation of the bus bar. But that will be shown when we go to the commissioning part of this webinar, or maybe that will be in part 2, because it seems like we are going towards that part 2, because we have 10 minutes left till the end of the webinar, and we have not covered all of it yet. So, and also I want some time for Q&A. Please do hold on to your questions now, or provide those questions to us in a written form. I think the chat allows you to do that, question section allows you to do that, and we're gonna respond to them afterwards, also in the written form, or go over some of them in part 2 of this webinar. I don't want to spend time on Q&A during this live presentation, so let's keep moving. So all of them are occupied. All of them go to the same battery when it comes to Nano system. Very important. Then you have smart ports. You have L1, L2, and L3. These smart ports are used for either generator, AC coupled PV, or smart load. Now, it's not like either or, well, once the system is commissioned. Whatever you commission the system with and whatever you configure these ports for, that's how it's going to be, unless you completely change your system layout, and instead of the AC coupled PV, then you decide to remove that AC coupled PV altogether and put in the generator, right? You cannot have, okay, 2 p.m. to 4 p.m. this is for AC coupled PV, and 4 p.m. to 6 p.m. this is for generator. No, it's for one thing and one thing only, and it cannot rotate between the modes of operations. Number 4, these are L1, L2, and L3 for backup loads. This is your backup ports. These are the ports that provide backup for your site in the case of a grid outage. These are also the ports that you use if this is off-grid application to output the power from the inverter to the loads. Then you have number 5. These are your grid inputs. You have L1, L2, and L3 here, as I was saying, here and on L1, L2, and L3, and here on smart ports L1, L2, and L3. Phase rotation matters. It matters a ton. And you check for both smart ports and for the grid. And this is where your grid connects. Then number 7, you have neutral bar, and number 8, you have ground bar, right? Okay. Just a reminder, there are 4 MPPTs in this case. The smallest quantity is 3 MPPTs, 2 inputs per MPPT. Now, with that reminder in mind, these are the rules and these are the other reminders. If 2 PV strings are connected to a single MPPT, the 2 PV strings must be identical in all aspects. And those aspects are listed right here, and this is a rule. No shading. The module type per string must be the same. Module quantity per string must be the same. String orientation in space, or each module in each string has to have the same orientation in space as all the other strings, right? Or all the other modules, sorry. And then MPPTs themselves are autonomous and independent from one another, and these, again, are specs carried over from one of the first slides where I was talking about the MPPTs. Just a reminder. APS transmitter, I mentioned before, and I said that, oh, and if you use the MLP behind the module, which is compatible with this transmitter, you'll be fine. Well, here are the compatible ones, RSDD15 and RSDS PLC. Seems to me that the latter is more popular than the former, but I don't know if that's actually the case. I don't have statistical data to work off of. And even if it was the case, I don't quite understand the reason why. But these are the 2 compatible models according to IP Systems technical documentation. If an external rapid shutdown system is used, the built-in transmitter must be disabled. So this, you cannot have this AP Smart transmitter and also, I don't know, some other receivers, or you may not have also optimizers working with AP systems. So whatever your MLP is you go for, on the behind the panels on the roof or the ground mount for that matter. If it's not any of these two, then you have to have your own transmitter. Then some of the tools that you're going to be using right here and on the left side, bullet points, and also the torque specs are given here. Spring clamps are there for the smart loads, backed up or smart ports, backed up load ports, battery ports, and PV ports. So for those, you don't need special tools, except for the battery and smart port, you'll need a flathead screwdriver. Flathead screwdriver is such that this inlet diameter and the screwdriver diameter are very close to one another. If that is not the case, if a very narrow screwdriver is used, once you start applying torque, really, downward force, which will create torque, you might crack this bottom piece or bottom portion of this inlet, and that will be a problem. So diameter should be as close as possible, and the inlet itself does not have a cylindrical shape. It has more of a shape of a cone, but which ends in the line. That's why I'm saying the flathead screwdriver needs to go in to accommodate for that shape, because it has to be in such a way that the torque is applied fully onto the entire clamp and not only on the portion of it. Because if it's applied only on one portion of it, that portion is going to crack open. Ask me how I know. I managed to break one. Not on this particular inverter, but the one that we have in the lab. But previously, that has happened to me. So words of wisdom from me to you: do use appropriate tools. If you don't feel comfortable, if you see that plastic whitening here because of the tension applied to it, or if you even see like the tiniest deformation, right? Tiniest deformation indicating stress mark, let go of it and try to use a different tool. Now, as far as how to use the conductor in there, the conductor must have its insulation removed by about 0.5 inches. Then that insulation is placed within the bottom of the port, and then clamp is closed. One more thing, when you are opening it or closing it, initially it will arrive in neutral position. So in neutral position, it moves up and down. But then if you're closing it, once it moves down, there's one more step. It needs to click in place, right? And then when you're opening it, you lift it up, it clicks, and then it's in neutral position. And then from neutral position, you need to put it in the actual open position. So that's another step that you need to do. So all the way up to open it and all the way down to close it. And neutral position is not the indication that it's actually closed or open, regardless of where the clamp is oriented upwards or downwards. It has to click in place. And another thing, once you are done, once you have put the conductor in place and close the clamp, give it a gentle tug. Make sure that it's safely in place and it's not going to fall out. Then, stuff about communication. I know it's a ton, but I'm only gonna go over the things that matter to the standard installation, and I need to call it. That will be part 2 to this webinar because I have tons of things to go over, and unfortunately 1 hour is simply not enough. I don't know how else to say it. So we're gonna have part 2 of this webinar coming up. Please do join it. But for now, let's focus on this slide. This yellow arrow shows the communication board that is already there, and it has 2 ports, BMS1 and BMS2. BMS2 port is not to be used. BMS1, number 10, will be used to communicate from the inverter to the primary battery. So if you have one battery, that's your primary battery. If you have multiple batteries, the primary battery is the first one in the chain, the one that communicates to the inverter. Number 11 is for hardwire internet connection, right? So that's the thing. Then on the inverter, you have PA and PB ports. This is for parallel inverter communication. So starting with PB, you go to the PA of the second inverter. From second inverter's PB, you go to the PA of the third inverter, and so forth, all the way to number 6. Also, it's not shown here, but there are, let me see if I can find a pointer here. There are dip switches here, 2 of them. For the first inverter in the chain and the last inverter in the chain, those must be on, all the others should be off. If it's one inverter, that one is the first one or the last one. Depends on how you look at it. So obviously, it will be on. If you have 2 inverters, first one is the first one, second one is the last one, so both of them on. If you have 3 or more, first and last on, the middle one's off. Then CT ports, these, we don't use it at all because remember, we said that we have a meter and that meter communicates here. Where does it communicate? To this port, the meter port right here. How does it accomplish that? We're going to see in the next part. EMS, this is for pro package application only. DRM, unused. RS-45, unused. BMS1 and BMS2 already connected to this board, to which you are connecting to port number 10 with your primary battery. Digital communication ports, only 2 of them are used, or 2 pairs of them are used. EPO plus, EPO minus. So you connect your external emergency power off switch or a button here, and Gen DO2 plus and Gen DO2 minus, which I mean it's not really plus and minus, it's a dry contactor for 2-hour start, but you connect those cables right here for generator auto start. Everything else is not used, at least for now. And do I have time for one more slide? Yes, 2 more slides actually. So EPO plus, EPO minus, this is what I meant. Built-in switch right here. Both of them are active. If either one is activated, rapid shutdown and the EPO of the inverter is initiated. And one more thing. Initiating EPO on the inverter doesn't mean that the EPO will be initiated on the battery. I just want to make that very clear. We're going to develop a solution on how to do it and how to make so that one button initiates the EPO on both. But in a normal configuration, inverter connected to the battery, communication being there, power cables being there, auxiliary AC being there, pressing one of the EPO buttons doesn't activate EPO on both units. So for today, because this was scheduled for only 1 hour, I'm going to stop here. And next time, we're going to continue from this point, eSpire Nano meter, how to put it in. So 4 meters turns out it's 13.2 feet. So how to put it in, what to look out for, what should the orientations be, stuff like that. We're going to start from the meter, and we'll go all the way through this information to the commissioning and to the inverter configuration and to the thank you and Q&A. So please do join the next part of this webinar, which I don't know when it's going to be scheduled for, but it will be scheduled for sure. Please do join it, and see you next time.